All right, so the next thing we're going to do is look at things that happen, consequences of special relativity. And two of those are time dilation and length contraction. What do I mean by this? These happen when, by this I mean time dilation and length contraction happen when things move at relativistic speeds. So by relativistic speed, let's write that down. Relativistic speed is when the velocity of an object, v, gets really close to the speed of light, that's c. And remember, c is 3 times 10 raised to the power 8 meters per second. So this is c. And when something moves at a speed close to c, we say it has a relativistic velocity. So in solving questions like this, you may be giving objects moving at 0.8 c, 0.9 c, 0.9 c, 0.995 c. These are all relativistic velocities. So time dilation and length contractions are things that happen when things move at relativistic velocities. And this is one of the consequences of pressure relativity, which says that the faster something is, the faster an object moves, the slower time passes for that object. So the faster an object moves, the slower time passes for the object, and also the shorter it becomes. So these are consequences of length contraction. So what I'm going to do is trying to explain the mathematics behind this to get a mathematical expression for this, the formula you've seen on it. So we're going to look at two cases, and I'm going to set up something called a light clock. A light clock, like literal light, L-I-G-H-T. This is a light clock. So this is our first one here. What we have here is two mirrors. I'll call this A and I'll call this B. Perfect mirrors, right? So what we're going to do is introduce a pulse of light, a single beam that will travel and bounce between A and B, up and down, up and down, up and down. So it will move from, let's say, start from A. It will move from A, hit the mirror B, come back down, perfectly elastic, no loss of energy, up and down. And the length, the distance between A and B is L. Is L. So we know L to be the distance between A and B. And we know that since there's light, it's going to move at C. That's 3 times 10 raised to the power 8. So let's ask ourselves, how long will it take for the light to go from A to B and back to A? Remember that speed is distance over time. So speed is distance over time. Maybe speed is distance over time. So time is distance over speed. So going from A to B and back to A, it covers a distance of 2L. So we're going to call this time T naught. So T naught is going to be the distance covered over the speed of that light horse. So the distance is 2L. Since we're going from A to B, that's L, and B back to A, that's another L. So 2L over the speed of the object, so that's C. So we keep this aside, we're going to use this later. So this is our first case, our stationary light clock. The next thing we're going to look at is what happens when our light clock begins to move, begins to travel. So let's say we put the clock on a spaceship and this spaceship moves past our observatory, let's say on Earth. Okay, we're going to need to draw a time lapse of what happens. So I have my two clocks. I have to redraw it. Okay, so I have my two clocks. So what's really happening here is something like a time lapse. You know how in a piece of film, if you unroll a piece of film, you see like still images of the person moving from his hand going down, from it going up. So this is like still image. And the spaceship containing the light clock is going from left to right this way at a velocity v. Okay, so we have a prime, and let's say a prime prime, b prime, and b prime prime. All right, so this is, let's say this is the light clock at the beginning, then it moves left to right, and we took snapshots. We're taking snapshots of the light clock and laying them beside each other. So as it goes, as the spaceship moves past us, the light is going to go from A. It's going to hit the mirror B. Okay, remember these are mirrors. Okay, so they don't absorb the light, they just reflects it perfectly without losing energy. So it goes from A to B, back to A. Perfectly elastic without losing energy. And the distance between A and B is still going to be L. That doesn't change. Still going to be L. But then the question we're going to ask is, how long is this distance A to B prime? How long is distance A to B prime? So we know it will still be the same concept we're doing, but this time it's not going to be T. Not, we're going to use T. Just T. Just T. So T is going to be the distance of a speed. All right, so the spaceship moves. This A to B is L. It moves with velocity v from left to right. So we're going to find what is the distance A to B prime. We're still using speed as distance over time, so distance is going to be speed times time. So the distance A to B prime, let's do it like this, is going to be the speed times the time. So what's the speed of the light pulse? That's c. And what is going to be the time taken for it to go from A to B prime? We know that's going to be half of the total time going from A to A double prime. So that's half of the full cycle. So we can say it's c times t over 2. So A to B prime is c times t over 2. And A to A prime, another important distance, is going to be still speed times time. But recall that we have a spaceship moving at velocity v, not light. So this distance A to A prime is going to be equal to v times t over 2. All right, so we have all we need, and we're going to look at the continuation of this later on. So this is for our moving light clock. All right, so we set up equations for our stationary and our moving light clock. So we're going to draw a very important triangle that's going to help us to understand why that formula looks the way it does. So this triangle is, if you remember the shape we drew in the last video, this is A prime, and this is B prime. So this is 1/2 cycle from the bottom to top. It will work the same way if you go from top to bottom, but we're going this way. A to B prime is the distance that light covers when moving in half a cycle. So remember that's speed times time, so that's c times t all over 2. A to A prime is the distance covered by the spaceship in that time. So that spaceship is going to be, that distance is going to be v times t over 2. And A prime to B prime is the distance between the mirrors. That's L. We're going to do a simple Pythagoras. So that gives us the hypotenuse squared, c squared, is equal to a squared plus b squared. Let's substitute in c. C is the hypotenuse, so that's c t over 2. C t over 2 squared is going to equal to a squared, let's pick aside vt over 2, vt over 2 squared plus b squared, that's l squared. Let's expand this. So c squared t squared over 2 squared is going to be equal to v squared t squared equally over 2 squared plus l squared. We're going to multiply 3 by 2 squared is 4, so that cancels out. So it says multiply 3 by 4, so that cancels out. That's going to give us c squared t squared is equal to v squared t squared plus, well, this is t now, plus v squared t squared plus 4l squared. Okay. Let's take this to the other side and leave l squared on one side. So that's going to be c squared t squared minus v squared t squared is equal to 4l squared. And if you look closely, you can factorize t squared out of this since they have common terms. So that's going to give us c squared minus v squared times t squared is equal to 4l squared. So what do we do from here? Remember from our stationary light clock, that's t naught is equal to 2l over c. So what will happen if we square both sides of this? Multiply both sides by each other. So we're going to have t naught squared is equal to be 4l squared. Remember 2 squared is 4. 4l squared over c squared. So if we take this to this side, we have c squared t squared is equal to 4l squared. So this is what we're going to substitute on the right hand side of this equation. So let's go. C squared minus v squared t squared is equal to, remember, this is what we're substituting, c squared t naught squared, pardon me. So c squared t naught squared. Alright, we're going to divide both sides by c naught. If we do that, this cancels out, this cancels out, and we're going to end up with v squared over c squared. So let's do that. 1 minus v squared all over c squared times t squared is going to be equal to t naught squared. Let's go back to the top. So remember, we're trying to look for t, the new dilated time that happens when something moves at close to the speed of light. So that's going to be t squared is equal to t naught squared all over square root of 1 minus v squared over c squared. Pardon, I go ahead of myself. 1 minus t naught over 1 minus v squared over c squared. So if we take the square root of both sides, square root of this and square root of the whole thing, we're going to end up with t. This is our new dilated time is going to be equal to the square root of t naught squared is t naught. So we're going to have t naught all over square root of the square root of 1 minus v squared all over c squared. So that's how we end up with that formula for dilated time. T is the new dilated time. And t is always going to be more than t naught. T naught is the original time. C is the speed of light. And v is the velocity that the spaceship or the astronaut or the subatomic particle is traveling at. So that's what we have. Analogously, there's for length contraction it's a bit similar. Just that your new length L is going to be L naught times the square root of 1 minus v squared over c squared. So the formulas are similar for time dilation and length contraction, just a little bit different. Because the dilated time is more than the original time, and the relativistic length, that's the length that happens when it moves at a relativistic speed, is going to be less than the original length. That's why these formulas are a bit different. So let's move on and tackle some questions on this.